Okay, so here is our problem on velocity of a plane. It says a plane is traveling at a speed of 360 miles per hour on a bearing of 270, that should be 270 degrees, sorry. All right, but notice it's a bearing. If you haven't watched the bearing video before doing this, stop right now, go back. The video will be titled something like an introduction to bearings or something like that. Watch that video. Don't continue. This will only confuse you at this point. Okay, go back, watch that video, and then resume this one. A plane is traveling at a speed of 360 miles per hour on a bearing of 270 degrees from Chicago to Salt Lake City. Salt Lake City's in Utah. If a 30 mile per hour wind is coming out of the northeast on a bearing of 225 degrees, what is the resultant speed and direction of the plane? So this is a velocity problem, right? Okay, because we're talking about speed and direction. So resultant speed and direction, that's what we get when you take the speed and direction of the plane and you affect it with the speed and direction of the wind, right? Because if a plane, and again, I'm not a physicist, I don't claim to be, but if a plane is traveling in a certain direction and a wind is traveling in a certain direction, even though this is a mighty plane and it's traveling very fast and it's very heavy, wind will still have an effect on that plane because it doesn't have that friction with the ground and so on and so forth. Again, not a physicist, don't quote me on that, but that's the idea, okay? So here, if we go with our coordinate plane, right? Now we have our x and our y axis here, okay? Just as reference points for these movements. Now again, bearings are measured 0 degrees, 90 degrees, 180, and 270. So when we're dealing with aeronautics, when we're dealing with planes in the air, we use this measuring system to show us what direction these are actually heading in, and then we convert those angles into standard position measurements before we do our calculations, okay? So this plane is traveling 360 miles per hour. Now, the speed is our magnitude, and magnitude is length. So the longer the vector, the faster the plane, okay? So if let's start in Chicago right here. Wherever it starts from, that's going to be our origin. Traveling a 270 degree angle or 270 degree bearing, I'm going to do this, okay? So I'm going to draw a relatively long vector because it's traveling at a relatively high rate of change, rate of speed there. So we have this vector to represent the airplane, 270 degree bearing, all right? If a 30 mile per hour wind is coming out of the northeast on a bearing of 225 miles per hour, now, what does that mean? So that means on a bearing of 225, so here's 0, 90, 180, where's 225? It's somewhere between 270 and 180, right? Do the math there, take 225, which is somewhere in here, and subtract the 180, and you'll get an idea of where this is headed, right? But 225 degrees from here is halfway through this, we'll call that the third quadrant, yeah? Now this wind is only 30 miles per hour, so if I draw this thing like that, just for the sake of all of the discussions we've had about magnitude representing the length, and in this case speed representing the length, the longer the vector, the faster the speed. Does this even make sense? If I want a semi-accurate drawing, this doesn't make any sense. Because if this is 360 miles per hour, this can't be 30. That's this is roughly half that. This is 180 mile per hour vector right now. So 30 miles per hour is like that. Okay? That's about it. That's the speed of the wind compared to the speed of the plane. Okay, now it's going to affect it, but clearly it's not going to affect it that much. Okay, so just because this is a little bit more applicable, what happens when the speed of the airplane, or excuse me, the speed of the wind affects the speed of the airplane? I can take this vector And I can actually, let me copy it instead of just dragging that one over there. Okay. I can take this, oh, come on now. There we go. I can take this vector and I can add it to the end of that vector. That's what happens when you get a resultant velocity. You add one vector's initial point to the terminal point of the other, and then we connect that to the initial point. So this third vector that I'm drawing right now, that I'm going to change the color of, okay, let's make it green. This green vector is the resulting direction and speed of the airplane, which makes sense, right? The plane was traveling this way, the wind was traveling in relatively the same direction, right, to the west, if you will, okay, and it's pushing it down just very slightly. So instead of the plane traveling in the direction that it was supposed to be, it's actually going a little bit more south because that's the direction this wind is blowing in. So this green vector represents the resultant velocity, the length, and the direction of that vector, okay? I'm going to cut this one and we'll pick up numerically calculating those values.